Bam! Mr. Tarrou. In this example video, we're going to take a look at an interesting problem here. It involves the use and understanding of continuity at a point and L'Hopital's rule at the same time. So we have here functions f and g are differentiable, and g of 3 is equal to 5. G satisfies the function g of x is equal to x squared minus 9 over x minus f of x cubed for when x is not equal to 3. Given that the limit as x approaches 3 of g of x can be determined, so basically, you're looking at this and it's like, okay, this function basically has a domain of everything but x cannot equal 3, yet we're going to be able to analyze the limit as x approaches 3 of g of x. That limit's going to be something that we can find. That can be evaluated using L'Hopital's rule. Use that limit statement, the limit as x approaches 3 of g of x, to find f of 3 and f prime of 3. Now, for us to be able to evaluate this limit statement using L'Hopital's rule, there's lots of forms of indeterminate, but the expression needs to be in the indeterminate form of 0 over 0 or infinity over infinity, plus or minus, for us to apply L'Hopital's rule, right? That's when you recognize that you have that form of indeterminate, you take the derivative of the numerator and denominator separately, write yourself a new expression, and then try to analyze that limit as x approaches some value. And if it does, great, and if not, maybe repeat the process of L'Hopital's rule again. Well, f of 3, f of x is in our original expression of g of x, and we have to take into account that this expression, the limit of this, can be evaluated using L'Hopital's rule, so the limit of this expression has to be a form of indeterminate. What happens if we do plug in 3? If we do plug in 3, we've got sort of like we're doing our conditions check, basically. For L'Hopital's, if we think about the limit as x approaches 3 of x squared minus 9, well, we get 3 squared minus 9 is equal to 0. Okay, so the numerator is equal to 0, which means that the denominator, if we're going to be able to apply L'Hopital's rule to evaluate this limit, the denominator also has to be equal to 0. So the limit as x approaches 3 of our denominator, which is going to be, we're going to go, okay, we have to analyze this. We're going to go and plug in 3. Well, that also, to get that form of indeterminate form of 0 over 0, that has to be equal to 3. 0, excuse me, plugged in 3. We're going to add f of 3 cubed to both sides. Take the cube root of both sides, and realize, okay, boom, we got f of 3 is equal to 2. So we actually haven't analyzed the limit yet, but understanding that you have to check the conditions to apply L'Hopital's rule, we ended up finding out what f of 3 is equal to. So we'll make a little footnote up here, and we're good to go. Okay, so we recognize that we have the limit of the numerator and the limit of the denominator are both equal to 0, thus satisfying that condition of allowing us to use L'Hopital's rule. We're going to apply L'Hopital's, and using that L'Hopital's, we now have the limit as x approaches 3 of our numerator after taking the derivative, which is going to be 2x. Our denominator, which is going to be the derivative of 8 is 0, the derivative of negative f of x cubed, we're going to bring that 3 down and have negative 3. Now f of x squared times the derivative of the inside function, so times f prime. Okay, now we're going to evaluate this new expression as x approaches 3, and we get 2 times 3 over negative 3 times f of 3, which we now know is 2, squared times f prime of 3. Oh, okay, well good. We have that f prime of 3 notation showing up. That's one of the questions here that we have. Find f prime of 3. But how are we going to find f prime of 3? Like, what is this supposed to come out to? Well, that's where part of the name is continuity to point. The limit as x approaches 3 of g of x is equal to what? Well, we're told that f and g are differentiable. And if a function is differentiable, it is therefore continuous. So while maybe we're thinking like a removable discontinuity, maybe you can't evaluate this expression at x equals 3, but we've just created like maybe a piecewise function. Like, okay, this function has a hole in it. Let's just go ahead and plug it with a piecewise function, how that can do when you have a hole in your graph. And if we're told that f and g are differentiable, then we're basically from that, and just to save some space, you'd have to maybe write this out on an AP test, but g is differentiable, and therefore, since we have this statement, since g is differentiable, the limit as x approaches 3 of g of x also has to be equal to 5, right? For continuity to point, the two-sided limit has to exist, which is what we're about to find. The function has to exist, and the function's value and the two-sided limit value have to be equal, continuity to point. So we know that the limit as x approaches 3 of g of x needs to come out to be a value of 5. And now we have an equation with only one known. What is f prime of 3? Now, how do we even know that f prime of 3 exists? I mean, a function can be continuous and yet not differentiable at a point. How do we know that f prime of 3 is not a sharp bend, where the limit as x approaches 3 from the left of, for your derivative, is not the same as a limit as you approach 3 from the right for your f prime function, your derivative function? Well, once again, we're told that f is differentiable. And so since f is differentiable, therefore f prime of 3 is going to, exist. We're almost done. We're going to multiply, have the fact that this is 6 divided by 5, so we have 6/5 is equal to, we're going to multiply all this over to the other side, -3. I guess we really don't need to. Let's not do that. That's silly. We're going to have 2 times 3 is 6 over -3 times 5. F prime of 3, or excuse me, f of 3 is equal to 2. And now we're going to just also not just divide both sides by 5, but multiply the f prime of 3 over to the other side. And we get 6 over, we get 4 times 3 is -12, and -12 times 5 is -60. And we get -1/10. And I'm going to make sure that I did not do some kind of silly error here. And that is the end of our example. So there's an interesting problem that makes sure that you understand what L'Hopital's rule is, you understand the condition checks for applying L'Hopital's rule, and you can work through your problem there and understand how to work it out because you remembered the definition of continuity to point. I'm Mr. Tarrou. Bam! Go do your homework.